Hello, in this video I will be discussing the idea of meso compounds. These are special kinds of stereoisomers that are not chiral. Now, you might say, well, how can you have a stereoisomer that's not chiral? The fact is, there are several ways you can do it, and one of them is by having meso compounds. So what is a meso compound? Very specific definition. A meso compound is an achiral molecule, so in other words, it does have a plane of symmetry somewhere in it, so that it's not chiral, and yet it has chiral carbons within it. What? How can that be? How can you have chiral carbons in a molecule and yet have the molecule not chiral? Well, the answer is if you have two chiral carbons in the molecule and both of them are mirror images of each other, then there's a plane of symmetry between them, and so therefore the whole molecule is not chiral. So it's like two ands in the same molecule. Both of them clearly are chiral, but if they're mirror images of each other, then the whole thing has a plane of symmetry and therefore is not chiral. That's the idea of a meso compound. So, like I said, this can only happen if the chiral carbons within the molecule are the mirror images of each other. So there's a plane of symmetry. Okay, so here's an example. Now, first of all, this compound that I've drawn is not a meso compound, so I'm just doing this to illustrate the point that some are and some are not. The thing to notice here is that this carbon is a chiral carbon. It has an OH, a hydrogen, and a methyl. This carbon is a chiral carbon. It has an OH, a hydrogen, and a methyl. So the same three groups on this carbon as on this carbon. That's necessary to be in a meso compound, but it's not the only thing that's necessary. The other thing that's necessary is that there's a plane of symmetry. And in this particular case, there is no plane of symmetry. So this is a chiral molecule. In other words, this plane right in the middle is not a plane of symmetry because the methyl doesn't reflect into an OH, and this OH doesn't reflect into a methyl, and so on. But we have to be careful because you also have to think about, could we rotate around that central bond and have the molecule then become achiral? In other words, could we, by rotating it, give it a plane of symmetry so that it's not chiral? And if it's not chiral in any of its rotational isomers, or as we learned before, they're called conformational isomers, if any of the conformational isomers is not chiral, then the whole thing is considered to be not chiral. Okay, so let's try rotating this bond 120 degrees forward. So we'll bring the methyl group down to where the OH is, we'll bring the OH back to where the H is, and we'll bring the H up to the front and see if that gives it a plane of symmetry. So if we can rotate around the central bond and make it have a plane of symmetry, then the compound will be considered to be achiral. Okay, so here is the molecule I was talking about. Notice we rotated the hydrogen from the back to the front. So it comes there. We rotated the methyl from front to down here, and we rotated the OH back to the back. So this is the same thing as this, just rotated by 120 degrees. Now do we have a plane of symmetry? Well, the methyl groups reflect into each other, but this hydrogen doesn't reflect into that OH, and this OH doesn't reflect into that hydrogen. So this is still not a plane of symmetry. Let's try rotating it again 120 degrees around to the front. So the hydrogen comes down here. There it is down there. The methyl goes up to the back. So there it is back there. And the OH goes to the front. See, there it is in front. So now, is this a plane of symmetry? And the answer is no. Even though the OHs reflect into each other, this hydrogen doesn't reflect into that methyl group, and this methyl doesn't reflect into that hydrogen. So again, no plane of symmetry. In fact, no matter how you rotate it, you will never find a plane of symmetry in this molecule, so it is, in fact, chiral. Okay? Now, just for completeness, let's assign R's and S's to this molecule. Now, I've drawn it in such a way that the hydrogens on both carbons are already pointing back away from you. They're on the dotted line, so that makes it easy. Just go 1 to 2 to 3, and 1 to 2 to 3, and you give it R's and S's. So go ahead and do that. See if this carbon is R or S, and then if this carbon is R or S. Take a minute and do that. Okay, so it turns out they're both R. 1 to 2 to 3 is a clockwise rotation around that carbon. 1 to 2 to 3 is a clockwise rotation around that carbon. They're both R, which it tells you right off the bat that this can't be a meso compound. Just a little bit of a preview here, because if it's RR, then its mirror image must be SS, which means it's not the same as its mirror image, then it has to be chiral. What do we say about meso compounds? They're achiral. In other words, they're not chiral. Let's go ahead now and draw a mirror image. So imagine a mirror right here. This molecule is looking into the mirror. What does it see on the other side? Well, this methyl is going to see a methyl here. This hydrogen is going to see a hydrogen here. This OH is going to see an OH there, and so on. So go ahead and draw the mirror image. And then I'll switch to the next slide. There it is. So notice this methyl reflects into a methyl in front. This hydrogen reflects into a hydrogen in back. This OH reflects into an OH down there. This methyl down here reflects into a methyl all the way over there. This OH reflects into an OH all the way over there. This hydrogen reflects into hydrogen all the way over there. So these are mirror images. Hopefully you can study those a little bit and see that they are in fact mirror images. Now what I want you to do is assign R's and S's to these. So give that one an R or an S, give that one an R or an S. You probably already guessed that since they're mirror images and that one's RR, this one's going to have to be SS. But go ahead and do the 1 to 2 to 3 and go around the central carbon and see if it's indeed SS. Now let's look at the next slide. Yep, it is in fact SS. And if you're still not figuring out how to do R's and S's, ask me and I'll go over it with you again. Now, I've drawn a third molecule here. How is this one related to the other two? Well, notice that I've kept this carbon the same. So we have an OH in front, hydrogen in back, and a methyl down. OH in front, hydrogen in back, methyl down. So these two carbons, I think you can see, are exactly the same. These two carbons, on the other hand, I have switched two groups. I've kept the hydrogen in back, keeping it easier to do R's and S's, but notice that the methyl and the OH here are switched. So it's OH up and methyl down. Here it's methyl up and OH down. So I switched two groups. What does that mean about the configuration? It must switch to the opposite configuration. So this one stayed the same. This one switched to the opposite. So go ahead and do R's and S's on this, and we'll see what we get. Notice this is an R, as it should be, because it was an R up here, and we kept it the same. Again, 1 to 2 to 3, clockwise around that carbon, that's an R. This one, 1 to 2 to 3, counterclockwise around that carbon, so that's an S, as it should be since we switched two groups. Anytime you switch two groups, you get the opposite configuration. Now, notice, in this particular conformation, there's a mirror plane. This OH reflects into that OH, this H into that H, this CH3 into that CH3. So this is not chiral. So this is an example of a meso compound. Again, just for completeness sake, go ahead and draw the mirror image over here. Now notice that this OH reflects into that OH, this hydrogen into that hydrogen, this methyl into that methyl, this methyl over here into that methyl over there, and so on. So this is the mirror image of that. Study it for a minute, make sure you believe that they're mirror images. But you'll notice something special here. Not only are these mirror images of each other, but they're also identical to each other. So what do we know about compounds that are identical to their mirror image? They're not chiral. So again, we see that this is a not chiral molecule. And if they're identical to each other, we really shouldn't draw it twice because it's the same molecule. You don't draw the same molecule twice unless you're going to somehow specially label. Notice that these are the same as each other. And you can go ahead and do R's and S's on this, but it better come out to be RS since this one's RS and it's identical. This is also going to come out to be RS. Now notice that it's this carbon, which is S, reflecting into that carbon, which is R, as it should since it's a mirror image of it. And this carbon, which is R, is reflecting into this carbon, which is S. But notice that even though it's this carbon reflecting into that carbon and this carbon reflecting into that carbon, these two molecules are still the same molecule as each other, exactly identical in every way. So they're not two different molecules, they're the same molecule. Now I want to show you this using some models here. So first of all, take a look at this model. The way I've constructed it is on this carbon I have a black ball, a red ball, and a white ball. And on this carbon I have a black ball, a white ball, and a red ball. So the same three groups on this end as on this end. And I've constructed it in such a way that if I line up the red balls, then the white and the black balls don't line up. So this is not a plane of symmetry. It certainly reflects this red ball into this red ball. So in that sense it's a plane of symmetry, but then the black ball doesn't reflect into a black ball over here, and the white ball doesn't reflect into a black ball there. Now we can rotate it, as always. If you're not sure if it's chiral or not, try rotating it and see if you can get it into a conformation where it does have a plane of symmetry. But if we rotate the red balls away from each other to get the white balls to line up, then obviously the red balls aren't mirror images of each other. And if we rotate it to get the black balls lined up, still no plane of symmetry. And for that matter, even if we look at staggered conformations, no plane of symmetry in any of those. So this is a chiral molecule, does not have a plane of symmetry. This would be like this molecule right here, and I happen to have its mirror image here. Also, if I line up the red balls so they reflect into each other, the white and the black doesn't, and if I line up the white balls so they reflect into each other, then the black and the red don't. So again, this is not a plane of symmetry, but notice that these two are in fact mirror images of each other. So the red ball on this side lines up with the red ball there, red ball down here lines up with the red ball down there, white balls obviously reflect into each other, and so on. So these are in fact mirror images, but they're not the same as each other. No matter how I twist and turn them, I can never make them look the same as each other. Therefore, they are enantiomers. One is the RR, and the other one is the SS enantiomer. So these are chiral. Just like any other chiral compound, it's not the same as its mirror image. This, on the other hand, the white balls reflect into each other, the black balls reflect into each other, the red balls reflect into each other. So this is an achiral molecule. It has a plane of symmetry, and yet it still has chiral carbons. So this is an example of a meso compound. And notice that I can twist it in such a way that it does not have a plane of symmetry. In this conformation right here, no plane of symmetry. And in this conformation, no plane of symmetry. But remember the rule, if you can rotate it so that it becomes achiral, then the molecule is considered to be achiral. So this conformation is chiral. Okay? There's no doubt about it, it does not have a plane of symmetry. But remember, rotation around single bonds is happening all the time. And so this molecule certainly, on average, will be achiral. Half the molecules will be one, and half the molecules will be the other. And some of the molecules will themselves have achiral, will have plane of symmetry. So the whole substance is considered to be achiral. So, question, are these two molecules up here, are they chiral? And the answer is yes, they are, because it's not the same as its mirror image, or thinking about it the other way, it has no plane of symmetry. So they are chiral. Are they enantiomers? Well, yes, they are, because they're mirror images, but they're not the same as each other, so they are enantiomers. So yes to both questions. Now, are these two chiral? In fact, it's almost wrong to say these two, because remember, they're the same thing as each other, so you really can't refer to them as two different things. But this molecule, are they chiral? And the answer is no, not chiral, because it has a plane of symmetry. And of course, this one does too, since it's the same thing as that one. And saying it another way, they are mirror images, but they're the same as each other. And any molecule that's the same as its mirror image is going to be achiral, in other words, not chiral. So are they enantiomers of each other? Well, they're certainly mirror images. But remember, to be an enantiomer, you have to be a mirror image, but also not the same as the mirror image. These two, the mirror images, are the same as each other, so they're not enantiomers. Nope, not chiral, not enantiomers, they are identical. And so, as I said, really, you shouldn't draw four molecules, because two of them are the same as each other. You shouldn't draw the same molecule twice, unless we're being very careful in labeling. Notice that these two are the same as each other. So really, there's only 3 stereoisomers here, not 4. So this is, again, a meso compound because it has chiral carbons. Certainly that's chiral, it's R, and this is chiral, it's S. But the whole molecule is achiral, so it's called a meso compound. And, again, notice that there's really only 3 stereoisomers here, not 4. And so the 2 to the n rule is not true in this case. This is one of the exceptions to the 2 to the n rule. So anytime you have meso compounds, you're always going to have less than the number predicted by 2 to the n rule. Now, I've drawn a bunch of molecules here. All of these are pairs of diastereomers. So these two are diastereomers of each other, these two are diastereomers of each other, and so on. The point of this is, though, that in this case we have 2 diastereomers, neither one of which is chiral. Same thing here, neither one is chiral. Here we have a pair of diastereomers where one's chiral and one is not. Also here, one chiral and one not. And then here, both of these are diastereomers, but they're both chiral. And these are also diastereomers, but they're both chiral. So the point is that diastereomers can have any relationship to each other. As we saw in a previous lecture, diastereomers are different compounds in every way. The properties have no relationship to each other. And so it turns out it's very easy to have them both be chiral, have them both be achiral, or have one chiral and one achiral. So I've just given you some examples, and this will help us explore the idea of chirality and the idea of meso compounds a little bit further. So let's start with this pair of structures. This is obviously cis 1,4-dimethylcyclohexane, and this is trans 1,4-dimethylcyclohexane. Are they stereoisomers? Yep, they sure are, because they only differ by the fact that that's up and that's down. So they differ in space, not by what's connected to what. Are they mirror images of each other? Mirror images of each other? And the answer is no, they're not. No matter how you turn them like a pancake, or turn them 180 degrees like this, or however you do it, you will never make them look the same as each other. Mirror images of each other, so they are diastereomers, stereoisomers that are not. And yet, notice that this is not a chiral molecule because it has a plane of symmetry right down through the middle, as does this, also has a plane of symmetry right down through there. This one also happens to have a plane of symmetry right through there as well, but the fact is that there's a plane of symmetry, then it's an achiral molecule. So this is not a chiral molecule, this is not a chiral molecule, but they are diastereomers. So there's an example of 2 molecules that are diastereomers of each other, neither one of which is chiral. In fact, in this case, they're not even meso compounds because there are no chiral carbons here. To be a meso compound, you have to have chiral carbons, but still be achiral. This is not a chiral carbon because the 4 groups on it are a methyl group, a hydrogen pointing back there, a CH2, CH2, CH with a methyl, and a CH2, CH2, CH with a methyl. So this group on that carbon and this group on that carbon are the same as each other. If you have 2 groups that are the same as each other, then it's not chiral. Okay. In other words, you could not assign an R or an S to that carbon. You could not assign an R or an S to that carbon. Same thing here. That's not chiral, and that's not chiral. So these 2 molecules are in every way, shape, and form. They have no chirality whatsoever, and yet they're still diastereomers because they're not mirror images. It's that simple. These two are simple. They are different from each other, but they are, and therefore they are diastereomers. Okay. So study these two structures for a minute and make sure that you accept a couple things. One, they're stereoisomers. They're not the same as each other. They're not mirror images of each other, so they must be diastereomers. But again, notice that this is not chiral because it has a plane of symmetry right across there. So this OH reflects into that OH, this hydrogen reflects into that hydrogen, the CH3 reflects into that CH3. That's one of the beauties of the Fisher projections, is it makes it really easy to see if there's mirror images or not. This one also has a plane of symmetry right through here. So this carbon reflects into that carbon. So not chiral. So this is not chiral, this is not chiral. Now, question, is this a meso compound? And the answer is yes, because it does have a chiral carbon, has another chiral carbon that reflects the mirror image of it. So it has a plane of symmetry, and therefore it's achiral. So the definition of meso compounds is the molecule is achiral, but has chiral carbons within it. This also is a meso compound because it has chiral carbons, this one and this one, but has a plane of symmetry, so it's not chiral itself, so therefore it's a meso compound. Now let's think about this carbon. Is that a chiral carbon? And the answer is no, because it has two groups the same. This group up here is the same as this group down here, so therefore not four different groups, so therefore it's not a chiral carbon, so that carbon is not a chiral carbon, even though it's drawn in a Fisher projection, so it kind of makes it seem like it should be a chiral carbon just because it's drawn that way. Just because it's drawn as a Fisher projection doesn't mean that it's necessarily chiral. In this case, it's not. Same thing here, that's not a chiral carbon for the same reason. Okay, let's look at these two molecules now. What's their relationship? Well, they are certainly not the same as each other. One's cis and one's trans. They are not mirror images of each other, so therefore they are diastereomers. Okay, they're stereoisomers. They differ only in arrangement in space. This carbon's up and that carbon's down, but they're not the same as each other and they're not mirror images, so therefore they are diastereomers. And we learned in a previous video that cis-trans isomers are always diastereomers, and these are no exception. They are. But notice that this one has a plane of symmetry right through here, and therefore this is achiral, whereas this does not have that plane of symmetry. If this were a plane of symmetry in this molecule, that methyl up would have to reflect into a methyl up over here, and it doesn't. There's a methyl down, and this methyl down would have to reflect into a methyl down over here, which it doesn't. So there is no plane of symmetry in this molecule, so this is chiral. This one is not chiral, so there we go, diastereomers, where one is chiral and one is not. Now notice that unlike these cases where these were not chiral carbons, this is in fact a chiral carbon right here, because it has four different groups. It has a methyl, a hydrogen, a CH2, and then a CH with a methyl, and a CH2, 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 and then a CH with a methyl. So four different groups here. You could assign that an R or an S. Same thing here, that's a chiral carbon. You could assign it an R or an S. And yet this whole molecule is not chiral, so therefore this is a what? A meso compound. It's not chiral itself because it has a plane of symmetry, but it has two chiral carbons that reflect into each other, and therefore is not chiral itself. This is not a meso compound. This is just a plain old chiral molecule, no plane of symmetry, does have chiral carbons, but they don't reflect into each other. If this is R, then this will be R. If this is S, then this will be S. This then is a chiral molecule, and it would have an enantiomer, and its configurations are going to be the opposite. So one of them would be RR, and the other one would be SS. These two are similar to these two, in that here we have a molecule with chiral carbons. So that's a chiral carbon, and that's a chiral carbon, but it has a plane of symmetry. So this is an achiral molecule, so this is a meso compound. This one, on the other hand, has chiral carbons. That's a chiral carbon, and that's a chiral carbon, but does not have a plane of symmetry, so therefore this is just a plain old chiral molecule. It would have an enantiomer, which I haven't drawn, and you might want to go ahead and draw the enantiomer of it, give it the R's and S's, and see that the R's and S's here are the opposite of the R's and S's here. So the enantiomers are mirror images of each other, but this is a diastereomer of this. Happens that this diastereomer is not chiral, and this diastereomer is chiral. So again, you may have one chiral and one not. Or you may have neither chiral, as we saw here, neither chiral, as we saw here, or you may have both chiral, as we've seen in this set down here. So notice that these are, again, stereoisomers of each other. They differ only by the fact that that's up and that's down. This is cis and this is trans, and so they are diastereomers of each other. This does not have a plane of symmetry, so it's chiral. It would have an enantiomer. Its mirror image would not be the same as it. This does not have a plane of symmetry either, so it's also chiral, and its enantiomer would also be different, where the 2 to the n rule does apply. You would have 4 total isomers here, 2 enantiomers, and then 2 more enantiomers, and diastereomers of each other. So again, diastereomers where they're both chiral. Same thing is true here. No plane of symmetry in this molecule, no plane of symmetry in this molecule. They're both chiral, but they're not mirror images, so therefore they are diastereomers of each other. This would have a mirror image enantiomer. This would have a mirror image enantiomer. So again, 4 possible isomers So the 2 to the end rule applies in this case. So hopefully this presentation has given you a little bit of familiarity with what meso compounds are. If you have any questions about that, of course, consult the book and or ask me questions in class. Thank you.